Thanks for the introduction, Stephen. So today I'm here to talk about. Can you hear me? Okay. Today I'm here to talk about phase transitions in the context of ultracold chemistry. Uh, sorry. Yeah. We'll start with a quick primer on what is quantum phase transition. We all understand what a classical phase transition is. So it's usually marked by uh, significant changes in the physical property of the system and characterized by an order parameter. So the prototype for understanding a classical phase transition is the Ising model with nearest neighbor coupling. So if you consider the least energy state of the Ising model, it happens to be the ferromagnetically ordered state with the spins all pointing in one direction. And this is the only state which is populated at absolute zero temperature. Now, if you increase the temperature of the system, entropy sets in and the free energy increases as a function of temperature and the order parameter like that. Okay. So what happens due to the increase in the temperature is that the order in the system is destroyed and the free energy goes from a double well to a single well structure about a characteristic temperature. Okay, so this is, and the order parameter, in this case, which the magnetization, dies down to zero as a function of temperature. Okay, so this is all thermal fluctuations as a function of temperature. Now, if you consider the quantum version of this model and add an extra term which corresponds to a transverse spin, you induce quantum fluctuations in this system, which also destroys the ferromagnetic order. This does not require temperature. There is no thermal fluctuations involved. So in some sense, what you're doing is you're giving the system another dimension to kill the order. And in this two-dimensional phase diagram, if you may, a classical phase transition corresponds to the vertical line over there, and the quantum phase transition corresponds to this horizontal line over there. Okay, so the key takeaway from this slide is that a quantum phase transition is characterized by a change in the nature of the ground state of the system. Okay, now we'll come back to quantum phase transition a bit. For now, we'll discuss the dynamics around a Feshbach resonance, which is what ultracold chemistry starts with, I guess. So I'll run through this quite quickly because you all know what this is about. So you have two atoms, and the collision between two atoms is characterized by a scattering length, and you can modify the scattering length using a magnetic field, using a Feshbach resonance, and the functional form of the scattering length goes like that. And if you have the scattering length like that, you can model a two-body collision using a contact potential of that sort. So this is all something we know, I believe. Okay, so if you want to understand the dynamics around a Feshbach resonance, you need to consider a Hamiltonian and propagate its dynamic. A many-body Hamiltonian, which describes this collision, will look something like this. So this is formidable, but we can try to break it into pieces. It's good to remember that the psi A dagger is the atomic creation operator, and that formidable term over there is a pairwise interaction which causes the collision, and ideally it should also lead to the formation of molecules. Okay, so that term, it only assumes two particle collisions, so that's the dilute limit, and also assume, it does not account for the fact that the collision time becomes infinite when the molecules are formed. Okay, so what happens is that the scattering length description of the many-body physics around a Feshbach resonance breaks down in this description. So what's the solution? The solution is that you put in the Feshbach resonance term by hand. So at its core, Feshbach resonance is hyperfine interaction, matrix element. So into this Hamiltonian, we put in that term by hand. So that term corresponds to killing two atoms and creating a molecule, and killing a molecule and creating two atoms. So the alpha parameter over there is determined by the Feshbach resonance. So, sorry, it's determined by the Feshbach resonance. Okay, now if in this Hamiltonian, if you retain just the Feshbach resonance term and consider spatial homogeneity, you'll just have the second term. Okay, now you have to consider the effect of ramping a magnetic field, and that looks something like that. So if you consider a linear ramp of magnetic field, that can be expected to change the energy of the molecule linearly, and it's easy to understand this using the simple Landau-Wigner picture, which is familiar, I believe. Okay, now so far so good. From here, we do a mathematical transformation, a pseudo spin transformation as we call, to get what is called as the Davis-Cummings model, which corresponds to a two-level system interacting with a path of photon. So in this model, absorption of photon causes an excitation. Now, mapping back to the model above, uh, absorption of photon is the destruction of molecule, and emission of photon is a creation of molecule. That's the only thing you need to remember from here. Okay, so now we discussed quantum phase transitions in the Davis-Cummings model. So I suppress the time dependence for now just to have a feel for this. The time dependence is in the gamma parameter over there. Okay. Through a lot of detailed mathematical sequence of mathematical transformations, you can reduce that in the mean field limit to a Hamiltonian like that. So that's the first quantized V of Q plus P, kinetic energy plus potential energy Hamiltonian. It's simple. Okay, so if you want to understand the detail of this transformation, that's what it is. I'm not getting into that. We can discuss in the coffee break maybe. The one thing potentially which helps to remember is that n is the number of atom pairs in the system, the starting number of atom pairs. Okay, so that's the mean field model. Now, if you consider just the potential term in this model, for gamma greater than 0, it corresponds to a single well. And for gamma less than 0, it corresponds to a double well. You can draw the parallel to the Ising model which I spoke about in the, to start with. So this corresponds to a second order quantum phase transition. The phase transition in this case can be understood if you put in this time dependence back. If you consider a linear ramp of magnetic field, atoms are converted into molecules. So that is the phase transition. Okay. So, and now if you plot the dynamics, so you take this Hamiltonian, propagate it in time, and plot the dynamics, the average number of molecules smoothly goes from 0 to 1 as you ramp the magnetic field. Okay, so this is all second order. Okay, yeah, that's an awkward orientation. Anyway, so now we want to understand the role of interactions apart from Feshbach resonance. So as I said, Davis-Cummings model is ignoring every other scattering event except for the atom-atom Feshbach resonance. So I can go into the details of why this is wrong theoretically, but I think it's important to understand or ask the question, what's the experimental relevance? So I'll give one example right now. I believe Professor Chin will talk about this in the afternoon session. So a three-body recombination event is not included in the Feshbach resonance, and this has been observed experimentally last year, 2 years before. Okay, and here you have a bosonic stimulation just coming from this three-body recombination event, which is similar to the effect of laser, so the stimulated emission in a laser. That's my understanding of it. Okay, so that means that the terms which you ignored in the Davis-Cummings model perhaps should not be ignored. Okay, so I'm not discussing the three-body recombination event, but what we are proposing is that a minimal model at least should include all the two-body interactions, which in this context is going to be the atom-atom Feshbach resonance, and all other two-body off-resonant terms, which is atom-atom, atom-molecule, and molecule-molecule. Okay. So now, the bold claim we are making is that that inclusion just corresponds to the inclusion of the last term over there. Okay. This is again a mathematical statement, and it follows from the number conservation property of the Davis-Cummings model. Okay, so if you consider the mean field Hamiltonian again for this model, you have the similar dependence, except that the fourth order term is now r plus g by n instead of g by n. As long as this term is positive, nothing changes. It's still a second order quantum phase transition. However, when G4 is less than 0, the fourth order term is less than 0, then you have to consider the next order term, and you get a first order quantum phase transition, which, as if you set gamma to a linear ramp, again converts atoms to molecules, except that this time you don't have 100% efficiency, even if you do it adiabatically, even if you do it in the limit of beta tending to 0. So the efficiency of this reaction cannot be made close to 100%, even in the limit of slow ramps. Okay, so So I've plotted a 2D phase diagram of how the inefficiency looks like as a function of the interaction parameter. The top region, the black region, is more efficient basically, and that's the second order phase transition. Okay, so that it's quantitative, but that's not so interesting. The interesting bit for a first order quantum phase transition is in the dynamics. So for a second order quantum phase transition, if you consider the molecular wave function as a function of time, so it starts off, so one thing, so you have the average number of molecules in the first plot, and in this, uh, the second subplot maybe, you see the projection of the molecular wave function onto a coherent basis. So you can see that it starts off as a blob at the center corresponding to 0 molecules, and as you ramp the magnetic field, it gets it spreads in the coherent basis and becomes more and more, it becomes thinner and thinner in time until it settles into something like that. So it settles into an infinitesimally thin circle across the whole 360-degree available angle. Okay, so this beyond phase you get is just due to number phase uncertainty, similar to what you have in Heisenberg uncertainty. However, if you do a first order quantum phase transition, the system goes through a sequence of exotic phases like that, and the number distribution oscillates around an asymptotic value, which is indicated in gray over there. Okay, and in the t tending to infinity limit, it settles into a macroscopic superposition of two coherent states, which is symbolic, or which resembles the Schrodinger's cat. So this is something which is known in quantum optics. This is of wide interest in the field of quantum optics, as I understand. It seems that in atom to molecule Feshbach resonance, this is possible to realize potentially. Okay, so that's the conclusion of this talk. The idea is that passage through a Feshbach resonance can cause both a first order and both second order and a first order quantum phase transition. And these behavior, the mean field behavior I showed, is all universal. So you could carry over to another model which has a similar mean field behavior. And the first order quantum phase transition selectively exhibits a certain quantum effects, such as the collapse and revival pattern which you saw in the wave function, and the selective formation of a quantum state which resembles the Schrodinger's cat. The future work is to get the experiments in the regime of net attractive interaction, which is required to get this cat state. And a lot of theoretical studies are potentially needed to understand the two-body scattering length, off-resonance scattering length, and applications in quantum sensing and metrology. It's something which will potentially be beneficial for the field, I believe. Okay, with this, I acknowledge my collaborators in Los Alamos with whom I did this work, and the University of Cambridge for funding me, and my college also for funding me. Thank you so much.
Thank you very much, Vijay. One question maybe for Vijay? Boy at the back. Catch.
Thank you. Yeah. You hear me? Oh, yeah.
Yeah.
I got a question about when you show when you add the other term to your Hamiltonian, yeah, like a Q6, yeah.
Yeah.
And then you said that we have the not second order but the higher order phase transition, yes? Or
I said first order, but okay.
First order,
Yeah.
okay. And you said we have the first order and the second order, and what thermodynamic quantity you measure that you can say that you have the first order or the second order? Yeah.
So that's the idea of a quantum phase transition, that there is
that if you said like you have the second order, that you measure the heat capacity and you can see, okay, I have the singularity in the heat capacity, then how do you know you have the first order or the second order? But you didn't mention what thermodynamic quantities you measure and have some singularities in this.
I'm actually not so sure about the measurable thermodynamic quantity, because quantum the classification of ordering comes from it's not as universal as, so Landau theory for classical phase transition is universal.
Yeah, it's universal, yeah, but when you apply for some Ising model or something like that one, and you measure like the heat capacity, you make it the second derivative,
Yeah,
and
I
you
know.
can see
Yeah.
the second derivative is singularity, and you can say, okay, I have the
Oh.
second phase transition. Yeah, when you
You mean purely mathematically, is it?
yeah.
Oh, then that's simple. I mean, it's as I said, it's the mean field model over here. Okay, so as a function of gamma, so about gamma equal to 0, you have a continuous change in the derivative for a second order phase transition and a discontinuous change in the derivative for a first order quantum phase transition. The question is what's the equivalent of latent heat, which you see in a first order quantum phase transition. Unfortunately, I don't have an answer for that.
Okay, thank you.
I think, yeah, that.
Thank you. I think one more question. Yes.
Thank you for the talk. I didn't understand actually. So you create a cut state, but cut state in this generalized coordinate Q you get from mean field. But what does this mean for experiment?
No, this is not created from a mean field. This is exact quantum dynamics. The mean field theory was only used to interpret to characterize the quantum phase transition. So these are all exact dynamics with on the Travis-Cummings model with I believe n equals 200 or 500 particles. This is n equals it's possible to evaluate. This is about n equals 200, I believe. Yeah. The radius of the circle is the square root of the number of molecules formed. Yeah.
And what is the angle actually?
No, that's just a generalized phase. So, okay. So, if you the way to think about, so you have the field operators. Okay. So psi dagger, for instance, if you consider the field variables is square root of n, the number of molecules, times a generalized phase. So this is a semi-classical mapping, and so the radius corresponds to the number of molecules, to the population, and the phase. So the phase comes because you have an equivalent of so if you consider n to be the position, you have a conjugate variable which is momentum, and so in some sense it's the phase is the conjugate variable to n, so the number of molecules, and I believe this. So I'm not sure exactly how the phase ties to experiments, but yeah, we can discuss this in the coffee break. Yeah, sorry. Yeah.
Okay, thank you very much, Vijay. So let's thank all the speakers of this session. And we have a quick announcement by Michael.